Let's start with a quick review. So we know that we have these objects which are the final stages of a star. When the star reaches the end of its life, the core turns into carbon, and then there are outer layers of helium and hydrogen which are burning, and the core's temperature has risen a lot. And as a result of a core which is very, very hot, the outer layers expand because of all the heat coming from inside. And as they expand, they cool down, and we have something which we call a red giant. Now, the question was that once the carbon has formed, what happens afterwards? The principles which we have learned so far predict that the carbon core is going to contract further. It's going to shrink because no nuclear reactions are taking place, and then the gravity dictates that it just keeps collapsing and heat up until the carbon ignites as well at 500 degree Kelvin, 500 million degree Kelvin. But the point is that there is another competing force. There's another competing factor which can stop gravity's crush without involving any nuclear reactions. So that's the important thing. That so far we were saying that the gravity is a one-way street. It just keeps crushing. And to stop it, you need nuclear reactions. But now I'm going to tell you, actually I told you last time, that there is another factor which can stop this. And that is the Pauli's principle or degeneracy pressure. This is Wolfgang Pauli who gave this principle. What's the principle? Let me just quickly recap what I said last time. It states that no two electrons can occupy the same shell in an atom. That's what you learned in chemistry. It is like the atoms have fixed seats and they can be occupied by one electron only. The first shell has two seats, the next one has eight, and so on. That's what they teach you in chemistry. Similarly, free electrons in an object, like if you have a solid, then it has lots of free electrons. The outer shell electrons are just free, they're just moving around. And that's true for the core of a star as well, because the core is very dense, so all the electrons are all meshed up. They don't belong to any atom. They're shared by the whole core. So free electrons then have objects have seats available to them like a movie or lecture theater. Farman, you have a question?
Yes, sir. It is unrelated to the lecture, but I was asking, sir, if you would be able to share the recordings.
Yeah, I'm gonna upload them today.
And sir, also the slides because वो
ठीक
रिवीजन
है,
वगैरह के लिए साथ
ठीक
साथ.
है, ठीक है.
थैंक यू सर.
So this,
अच्छा सर, सॉरी, एक और क्वेश्चन था. सर, आप काउंसलिंग आवर्स वगैरह में अवेलेबल होंगे, मतलब व्हाट टाइमिंग्स.
you wanna come see in office or
यस सर.
चलो next week में कुछ setup कर लें, Monday कर लें.
ऑलराइट सर, आई हैव ऑलरेडी ईमेल्ड. श्योर सर, मैंने आपको ईमेल कर दी, तो इफ यू कुड रिस्पॉन्ड.
ठीक है, ठीक है.
थैंक यू सर.
So, okay, so degeneracy pressure. So because of this thing, because of this Pauli's principle, there is a source, another source of pressure, which is unrelated to temperature. This pressure is not because of temperature. Doesn't matter what temperature you have, even if you have zero temperature or very high temperature, this pressure is just there. It doesn't care about what the temperature is. So as I said last time, that think of a lecture theater, the seats near the blackboard have less energy, and as you go up the row, the seats have more energy. If you cool down an object, all the electrons will settle into the lower row. That's what cooling down means, that you have less energy. Otherwise, at higher temperatures, they are dispersed at higher rows. If you squeeze the classroom, the seats available in each row are reduced, and all the electrons may not fit in the lowest row, even at the coldest temperature. So they have to move to the higher and higher rows. So the electrons will be forced to occupy higher and higher energy rows even at zero temperature. That means the electrons have motion even at zero temperature, which cannot be taken away from them in any way because of Pauli's principle. Because if you want to take that motion away, they will have to move down into the lower rows, but there's no vacancy there. So they cannot radiate away this energy. This motion which they have, they cannot radiate away. So the gravity cannot crush it to make it radiate away. Because remember, when the gravity crushes, you have to radiate away this thing. But this motion produces a pressure, so not temperature. There's no temperature because you cannot feel it, because this motion does not transfer the energy to your hand. And this is called the degeneracy pressure. So in summary, two electrons cannot share the same space while having the same amount of energy. So when you squeeze them a lot, they develop some inherent motions which cannot be taken away from them. It means it's not related to heat. This creates pressure even at low temperatures, called the degeneracy pressure. And this is exactly the reason why the solids are solid. This new source of pressure can fight against gravity. This source does not need temperature. Solid bits and metals are solid because of this very reason. That's why our tables are solid. This pressure increases as you shrink the object. And this is exactly the reason why Jupiter is not a star. It's a ball of gas which shrank, but since it was not very massive, its degeneracy pressure halted the shrinking before it could reach nuclear ignition temperature. So degeneracy pressure in most cases is not a lot. Well, it's a lot, but not enough for these very big, massive gases, clouds of gases. It's not enough to halt the shrinking. But if the gas cloud is not heavy enough, then the degeneracy pressure itself would be enough to stop it. At some point, the degeneracy pressure does stop the shrinking. It matters, then it just comes down to where it will stop it. So you start with this size, you shrink, and as you shrink, you heat up. Now there are two possibilities. Either as you shrink, you heat up, the degeneracy pressure is not able to stop the shrinking, and you reach the nuclear ignition. The other possibility is that you shrink, you heat up, but before the nuclear ignition starts, the degeneracy pressure balances the gravity. So it depends that which one happens first. So clearly, if the weight is less, then the degeneracy pressure will balance it before you can heat it up enough to cause nuclear ignition. While if the weight is large, if it's a very massive cloud, then the degeneracy pressure it increases as you shrink. So as it's shrinking, degeneracy pressure is going up and trying to balance. But before it's strong enough to balance it, nuclear ignitions happen because you need a huge amount of degeneracy pressure to balance a heavier cloud. So that tells us that there would be a boundary in terms of mass. That if you have a very massive cloud, then its fate is to shrink and start nuclear ignition and become a star. While if it's not a very massive cloud, it will fail and become a Jupiter. What's a Jupiter? A planet. Become a planet or any other solid body. And that limit you can calculate is about 0.08 solar masses. Atik, stop doing that. And this is exactly what we observe. So this is a theoretical prediction that if you have something which is less massive than 0.08 solar mass, the degeneracy pressure is gonna stop the contraction before the ignition happens. And if it's above this, then you're gonna have ignition and you're gonna have star. So the prediction is that there should be no stars below 0.08 solar masses. And this is exactly true. You can go around looking for star, look in your neighborhood, find what are their masses, and no one has been able to find a star based on the estimates which is lighter than this. So Jupiter, why it's not a star? Because it's much lighter than this limit. So it couldn't ignite. Jupiter is again a ball of gas, but sustained by degeneracy pressure. Earth is also sustained by degeneracy pressure. That's why it's not shrinking. Someone should have asked, if the gravity always shrinks, why the Earth is not shrinking? Because there's degeneracy pressure. It doesn't need nuclear ignition. If the sun didn't have nuclear reactions, it would also stop shrinking at some point, but it would be at a much, much smaller radius. It will have to be crushed first to a very high degree. But since nuclear reactions exist, before that crushing happens, as soon as the central core reaches 10 million, you have a new source of energy and the degeneracy pressure becomes irrelevant. Now, why we are discussing it right now? Because what happens in these stars at the end of their life, well, this is true for low mass stars. What do we mean by low mass? Where mass is less than 12 solar masses. Stars which are lighter than 12 solar masses. So you have, as the carbon core shrinks, its degeneracy pressure increases, and finally the pressure balances the crush of gravity. And just like in case of Jupiter, in case of regular stars, there was a limit related to hydrogen's ignition temperature that you had to have a mass larger than 0.08 solar masses for the degeneracy pressure to fail and the core to reach temperatures to cause ignition. Similarly, if you have a carbon core, so that was the starting core of a cloud, which was hydrogen. But if you are having a carbon core, then it has its own limit. And that limit is 12. If you have a 12 solar mass star, then the carbon core will reach the degeneracy pressure first before the carbon can start burning. So what will happen in these stars, that the core will never reach 500 million Kelvin. The degeneracy pressure itself will increase so much because of the crushing that at some point it will balance the crush of gravity. So what happens is this. If I draw the radius of the core and draw over here the degeneracy pressure, as in the beginning the degeneracy pressure is very less. As you decrease the radius, degeneracy pressure starts increasing. And then you have the gravity somewhere here, gravitational pressure, which is some other line here. As you decrease the temperature, decrease the radius, it's also increasing. But at some point, the degeneration pressure becomes larger than the gravity. So as the shrinking happens, and at this point, you will stop shrinking. So this happens in the carbon core, and such a core is called degenerate core. It's just like a stiff brick, which doesn't contract on compressing. A brick is stiff, but if you compress it hard enough, it's gonna break. But this degenerate core is so stiff that at least its own gravity cannot compress it. So it no longer shrinks or heats up. The core is now just hot because of its original temperature and cooling away in the sky, becoming a brown dwarf and finally fading completely. So what happens is this is essentially the cycle of a star. You have interstellar cloud, which is quite big, of several light year size, and because of gravity, it starts shrinking. And as it starts shrinking, the core becomes hot, and you have in the center a star, a protostar. So when in the protostar, when the core starts nuclear reactions, it becomes a star like a sun. And when the fuel runs out, it becomes a red giant. And when the helium starts burning again, the red giant shrinks a little and heats up a little, becomes a yellow giant. And when the helium goes away, helium is all used up, and the core is carbon, it becomes a red giant. And after some time, this red giant, this core, is so hot, it's giving off so much radiation that these outer layers, they just fade away. Because of the radiation pressure, which we discussed last time, they're just blown out. It's like, as I said, that you have a hot air balloon which expands to a very big size. But suppose you turn up the heat so much that the balloons are just withers away, it just explodes. So that's what happens. It doesn't really explode, it just melts away. And you have these gases going out. These are all the outer layers of the star, they are just blown away. And these outer layers, you can see them being blown away, and this is called a planetary nebula. This has nothing to do with a planet, it's a misnomer. When people first detected, they called it planetary nebula. It's not planet. So what you are left with at the center is this degenerate core. This core of the star, it becomes visible because the outer layers are gone. So the core, which was always hidden during the main sequence lifestyle, and we said that we cannot see it, it becomes visible. It just reveals itself. And what it is just this thing. It's just the original carbon which is left there, and there are no nuclear reactions happening. It's just a stiff brick made of carbon, which is very hot because at one point it was very, very hot. It had this nuclear reactions going on and it was shrinking, and which was causing it to be hot. But now no shrinking is happening because of degenerate pressure, and no nuclear reactions are happening. So it's just like a stiff brick which you have heated up to a very high temperature, and it's just cooling away. So when it reveals itself the first time, at that time, what you have is something exposed, which is very small in size. Why small in size? Because it was just the core, not the outer layers. And it's extremely hot. Why extremely hot? Because it had caused the temperatures required to burn the helium. So it's hundreds of millions of Kelvin, much hotter than the inner core of most stars, and certainly extremely much, many times, many orders of magnitude hotter than the outer layers of stars. This is the core, it's the inside. And even that heated up to temperatures higher than the ignition temperature of helium. So small in size and extremely hot. So it gives off light, but the light is not a lot because the core size is small, although the temperature is high. And it's just cooling away. It's not going to last. It's just cooling away. But when it reveals itself, it is very small and extremely hot. So what should we call it? Since it's very hot, so it's towards the blue side of the spectrum. Well, not really blue, as we discussed. This is the spectrum. This is the visible part. This is the visible part. It's giving me trouble. Let me draw it here. If this is the visible part, in the beginning, you have this red side. But when it's very hot, like this guy, which is millions of, it just covers the whole visible part. It's so spread out. There's so much light in all of the spectrum parts that the visible part is all just contained within a small strip of this big spectrum. So there's almost equal light in all of the visible wavelengths. That's why it appears white. And that's why we call it, since it's small and since it's extremely hot so that it appears white, we call it white dwarf. So now we realize that these stars, some of these stars, which we see up there in the HI diagram, plotted as white dwarfs, as small objects, less luminosity, but extremely hot. What they could be, these are actually the corpses of the stars. And what's going to happen to these white dwarfs? They just cool down over time. They have a temperature, so they give off radiation. And the radiation is going out, and as a result, they don't shrink. They just cool down. They're no longer gravitationally collapsing. So in the gravitational collapse, what happens is as you radiate, you heat up. But it's not gravitationally collapsing now because the degenerate pressure has stopped it. So it's just like a regular piece of coal. It's hot and it's cooling away. So when they cool down, the surface temperature is going to go down. And as a result, they will become red dwarfs. And when they cool further, they become very dim. So you can call them brown dwarfs. And finally, they will be just lump of coal just traveling around in the galaxy, not visible to us, but if you encounter them, maybe you can land over there and you will see that you have a big lump of coal, and which would be the corpse of a star. Well, the corpse has two parts. It has the central white dwarf, and it has this shroud, which are these outgoing gases. The white dwarf is inside, and when these gases just move away, then it's completely revealed. So as a result, these star parts, they are blown out, and this is revealed. And now we have like kind of a complete explanation of the HR diagram. And what it is just giving us different stages of the life of a star. And since there are trillions of stars up there, so we find all representatives. Some of them are in their youth, some of them are just being born, some of them are dying in their old age, so they are red giants, and some of them are already dead. So they appear to us as white dwarfs. But the life cycle is like this. The star enters the main sequence from here and spends most of the time in the main sequence. Then it becomes a subgiant, red giant, comes back when the heat becomes a yellow giant, and when the helium coefficient stops, it becomes a red giant, and then a red giant finally becomes a planetary nebula, which is going out, and this white dwarf is revealed, and the star goes down over here. This is the typical life cycle. In the main sequence, you spend 9 billion years as a red giant. You spend 1 billion years when you are getting out short of hydrogen and your core is just now running out of fuel, so it's shrinking. And then you finally you spend some time as a yellow giant, and finally you again when the helium flash begins, you again become a red giant, and finally this red giant is also blown away, and you become a white dwarf. So this slide tells you the main principles governing the structure of a star. It's the gravity which holds the star together, and pressure supports star against the gravity. So this red arrow is the gravity trying to crush it, and then you need some kind of a pressure to hold the star up. Pressure is created by high temperature in star's core. So the star's core has to be extremely high at high temperature. And high temperature causes heat to flow from core to surface. So the surface gets heated, and that's where the light is produced, which we see as the star's luminosity with the starlight. So all this heat which is lost because you still need to maintain this temperature. So there are two options. Either you crush, you become smaller to increase the temperature, but if you want to maintain the size, then this lost heat, whose tendency is to reduce the temperature, has to be provided somehow. So it's provided by nuclear fusions in core. And this nuclear fusion is provided by hydrogen burning. But the star is finally gonna run out of, the core is gonna run out of the fuel. If it's a low mass star, it's gonna become a white dwarf. But if it's a high mass star, something else will happen, which I'm gonna discuss in a short while. And this is what we also discussed, that the high mass stars require more pressure to support their greater mass, and greater pressure means higher temperature means higher luminosity. So faster fuel usage, and you run out of the fuel very quickly. So the high mass stars, and this is defined as about 12 solar masses, they meet their end differently. So why do they maintain their end differently? Because they have so much mass that the degeneracy pressure is not able to stop the crush of gravity, and the internal heating, because of the crushing of gravity, goes to very, very high temperature, and you can cross the temperature required to the binding of carbon, which is about 500 Kelvin, 500 million Kelvin. So you can cross that. It's just like if you have a Jupiter which is higher than 0.08 solar masses, or a Jupiter which is of the same size, same mass as Sun. So this is also a prediction. You will never find a planet which is of the same mass as Sun. Because what's going to happen is that its weight is so much that the degeneracy pressure will not be able to stop the crushing of gravity before the core reaches the temperatures that cause the nuclear fusion of hydrogen. Similarly, if the mass of the star is very high, the degeneracy pressure will not be able to stop the crushing of the core before the core reaches 500 million Kelvin. And that's when the carbon fusion starts. So in the high mass stars, in the beginning is the same. It's just the hydrogen which is burning, and it's just a main sequence star. It's just that the hydrogen burns at a very higher rate, and you have a lots of luminosity. But when it becomes a red giant, because when the core starts having this carbon, the carbon doesn't stop burning. Carbon also ignites. So what you have, unlike the previous picture where you had like a carbon core and then the helium shell and then the hydrogen shell. Here you have lots of shells. So you have uh, hydrogen outside. First you have non-fusing hydrogen, then you have hydrogen which is fusing, and inside you will have helium. Then you will have carbon core, but the carbon core will start burning and it will run out of the fuel. So carbon will run out as well. The carbon fuses and makes oxygen. So then oxygen, then the core becomes a core of oxygen, surrounded by a carbon shell, surrounded by a helium shell, and that's surrounded by a hydrogen shell. So the core crushes again. Oxygen needs even higher temperature, but since the star is so heavy, so oxygen starts burning. And oxygen produces neon. Finally, you run out of oxygen, and your core is neon. Neon surrounded by an oxygen shell, a carbon shell, and so on. Neon becomes magnesium, magnesium becomes silicon, and so on. Finally, you have iron made, and the central part of the core is iron. Now, you expect that the crush of the star would be so much that it will cause the iron to fuse. But iron is a very tough nut to crack. Because if you fuse iron nuclei with some other nuclei to create even higher nucleus, remember that you do not produce any energy. In fact, you will have to provide energy to fuse the carbon, the iron. Remember, the iron sits at the valley, at the bottom of the valley. So you go this way, you don't produce energy. You go this way, you don't produce energy. So you cannot crush iron to cause it to fuse. Because why do you fuse? Because you want to create some energy to balance the gravity. So with iron, that cannot happen. So iron is the final limit of which the core can be produced. And you cannot produce any further elements in the core of the star. So what happens? So you have a central core which is holding up all the gravity of the star. And so it has to have a very high pressure, but you have no source of energy. So what happens? So we know that there are only two possibilities. Either it keeps crushing and going up, but that's going to stop. That's our guess says that what should happen? The core will not fuse to produce energy because that's not allowed by nuclear physics, nuclear chemistry, but will keep shrinking under gravity. And as it shrinks, the degeneracy pressure keeps rising. And no matter how heavy the star is, at some final small radius, the degeneracy pressure will be high enough to balance against the gravity. Because remember, the degeneracy pressure it keeps rising as you decrease the radius. So finally, at some radius, you're going to balance the gravity and you will have a very crushed iron core left out, and it will probably reveal itself, and you will have uh, probably a white dwarf made of carbon, made of iron. But the reality is a bit more dramatic. And it's dramatic because of something called Chandrasekhar limit. So Chandrasekhar was an Indian student around in 1920, around 1925. He was from South India, but he used to live in Lahore. He used to study he completed his studies in Lahore in FC College. And then he had a scholarship for Cambridge. And in those times, people traveled, if they had to move abroad, they traveled by sea. So he was on the ship going to Cambridge. He was, I guess, around 24 years old at that time. He did this calculation, which is now known as Chandrasekhar limit, and he won Nobel Prize for this calculation, and he had lifelong contributions to astrophysics. But he won finally the Nobel for this calculation, and this calculation made him famous right away. And this is an extremely important concept in astrophysics, which goes by his name. So what's this limit? It says that there's a limit which is reached so that if the core has more mass than this value, electron degeneration pressure cannot stop it from shrinking. So this picture that no matter how much mass I have, I can keep shrinking. And finally, the degeneration pressure will rise high enough to stop the shrinking. This is not completely true. What he calculated was that if you have a gravitational body which is heavier than 1.4 solar masses, and it's made of normal matter where you have electrons. This degeneracy pressure of electrons, which was the reason these electrons were sitting on these higher and higher seats, is never going to be enough to stop this crushing, to stop the collapse. So a core heavier than this mass, and this mass is the limit, Chandrasekhar limit, cannot be stopped. So that means if I have a white dwarf, what's a white dwarf? White dwarf is just some body which is sustained by degeneracy pressure. A body sustained by degeneracy pressure. Chandrasekhar tells you that no body can be sustained by degeneracy pressure which is heavier than 1.4 solar masses. That means we should not be able to find any white dwarf which is higher than this mass. And this is actually true. You can do a check of white dwarfs, that how heavy they are. These are the masses given in solar masses. So Sirius B is 0.98, Procyon B, these are all different white dwarfs which people have observed. And you can see they're all less than 1.4. And actually, people have done a big survey, not even one white dwarf has been found which is heavier than 1.4 solar masses. So if you can't have this, and by the way, this happens because of something related to Einstein's relativity. So Bohr is just quantum mechanics or Pauli principle. And Einstein says something different. So you had these rows, and I said that as you compress, these rows go up because there are less seats here. So if you have 1.4 solar masses, you compress, these seats go up, you have so many electrons that you have to fit. It turns out that Einstein says that this speed cannot increase, speed cannot exceed. This is a rough explanation. And that's why there's a conflict. So you cannot sustain a pressure, an object which is higher than 1.4 solar masses. But what happens if you have, suppose you had a white dwarf, which was 1.3 solar masses, and you started throwing in some matter, and you throw in, let's say, 0.3 solar mass worth of matter. What's gonna happen? How is this guy gonna stabilize itself? Especially if it's made of iron. because it cannot even ignite what's inside. There's no source of fuel inside now. And Chandrasekhar tells you that even the Degenacy pressure cannot stop. So what's it's gonna do? Is it gonna become a point? That's the question which is at stake. And it's very relevant for high mass stars because in high mass stars, the cores are made up of iron. This is the symbol Fe, or maybe you can just write iron. And the core in these high mass stars is bigger, typically bigger than 1.4 solar masses. So what happens? So what happens is, in this case, you have all these neutrons, sorry. In the core atoms, you have these protons. Let me open notebook. So imagine you have this core, and it's just a lot of atoms. They're probably crushed down, but you have these protons, neutrons, neutrons. So this is like a nucleus, and there are electrons. Electrons are probably stripped out because so high temperature, and these electrons are moving. And the Chandrasekhar says that something has to happen. So what happens is that these electrons are crushed and they meet the protons. Remember, we had this reaction. The proton can go into positron plus neutron plus neutrino plus neutron plus photon, which is energy. And I can bring it here by changing the charge. So this is a possible reaction. It says an electron can combine with a proton to make neutron, and a neutrino will be produced with some light. So that's what happens. Electrons combines with protons, and it happens in a second, in a very, very short amount, when the degeneration pressure is so much that the Chandrasekhar limit has reached, and the whole system is very stable. Something has to give. In the whole core, this reaction just goes through like a fuse going off. The whole core suddenly turns into neutrons. And all the protons and all the electrons are gone. The whole core becomes a lump of neutrons, something which no one has, well, I mean, no one on Earth has observed this kind of a matter. It's like a very, very big nucleus with about 10 to the 37 neutrons. And no proton and no electron, a very strange kind of matter. And what happens during this? A huge amount of light is produced. And a lot of neutrinos are produced because all the protons in the core are gone. And for each proton which is eliminated, a neutrino is produced. Let me change the share. The electron combined with proton to give you neutron, gamma ray, photon plus neutrino. And core collapses to become a giant ball of neutrons. Density of the core reduces to nuclear densities. By the way, I forgot to mention that in case of I forgot to mention in case of this white dwarfs, because the white dwarf which is finally revealed, which is just the carbon core, but this carbon is so much crushed that it's extremely dense. A tablespoon of this would weigh many tons. It's so much dense. But this guy, when this happens, when core becomes a giant ball of neutrons, its density is that of nuclear densities, which is extremely high because like most of the atom is just empty. Nucleus is just a very tiny part of it. So everything is collapsed to so high densities, and the matter you get is a very strange matter. It's just made up of neutrons. Nothing with any chemistry or anyone has dealt with. And there are no atoms, nothing. It's just a big ball of neutrons. And a teaspoon of this thing, which is left, a neutron ball, by the way, it's called the neutron star, would weigh about 50 million tons. A teaspoon weighs 50 million tons. And the whole mass, so this is typically heavier than 1.4 solar masses. So if the sun was crushed to this size, the whole sun, not the core, the whole sun, at these densities, it will only have a radius of 10 kilometers, like smaller than this city. And the whole sun, we're talking about the whole sun being crushed to a size smaller than, it's just like a neighborhood of Karachi. It's so dense. And this should give you some idea how dense it is. And when this happens, something very dramatic happens, because what happens is that you had this core and then you had these outer layers. Suddenly, as they say in Urdu, पैरों से ज़मीन निकल गई. So this core, in a fraction of a second, when these reactions happen, it just becomes extremely tiny. So all these outer layers, they have nothing to hold them. So they all fall. And this produces, they fall onto this central core with a huge bang. And this produces a huge shock wave, which heats up this gas to such high temperature, which are unimaginable, billions of degree Kelvin. Not talking about millions, billions of degree Kelvin. Generating luminosities of the order of 100 billion solar luminosity. They burn with such high temperature that their luminosity becomes equal to 100 billion solar luminosity. And then they also just fly out because of this shock. But this thing keeps glowing for a few days to a few months. And when this happens, we say a supernova is born. Is born. So you suddenly see a star. Well, sometimes you see the star, sometimes you don't because it was so dim, but it is quite possible if it's in a nearby galaxy or in your own galaxy, you will see a star, and then one day it just shines with the billions of 100 billion stars. So equal to the luminosity of the whole galaxy. And it will keep glowing for a few days with that glow and finally fade away. When it will fade away, it will leave behind it a nuclear core, a neutron core. So you can say it's a white dwarf made of neutrons. But we don't call it white dwarf made of neutrons. We call it a neutron star. We will see it next time that how does it look like. It's not plotted on the HI diagram because it's something very different and it was only observed in 1960s. But this is what our theory says, that what a supernova is, what should happen. And we see supernovas happening. Chinese saw it 1,000 years ago. There was a supernova in our own galaxy, and there hasn't been any supernova in our galaxy since then. On average, we expect that there should be one supernova per century in our galaxy and in most typical galaxies. But just by chance, there hasn't been any. And as I told you, that one of our close neighbors, this Betelgeuse, it's expected to go supernova. When it does, no one knows. But if it does, it will be a very spectacular event. We will be able to see it very, very clearly during the day. And the nights will be all bright if it happens. So anyway, there are supernovas in other galaxies, which we regularly observe. So what you see is that you have a galaxy. And suddenly the galaxy has a glow at some point, and the galaxy's luminosity doubles. Because the galaxy was giving light equal to 100 billion stars, and now one of its stars is giving 100 billion stars light worth of light. So the galaxy doubles in its glow. And this happens very often because we have billions of galaxies under observation. So every night, every other night, you see a supernova going off in some galaxy. But again, how do we know that this is exactly what happens and it leaves behind it a neutron core? Well, first of all, we will see next time that we have seen this, the final corpse of these heavy mass stars called the neutron star. But also, this reaction, it's telling us that their neutrinos are produced. And neutrinos are not trapped in any of this gas. We learned that neutrinos just pass through. So if a supernova occurs, huge amount of neutrinos must be produced right at that moment. And if it's nearby, we should be able to catch some of them. We are running out of time. I'll tell you this story that uh, wait. It was in 1987. There was a supernova in our neighboring galaxy. Not in our own, but in our neighboring galaxy, which is our satellite galaxy, the Andromeda. Andromeda is a galaxy known for a long time. It was called the Andromeda Cloud, a very spectacular cloud, bejeweled, spiraling, and bright, which was, I mean, for the people in the past, this is how it looked like. It's just a cloud in the sky, and it's part of the stellar celestial sphere because it's just like takes part in them. It just doesn't change anything. Now we know it's our neighboring galaxy. I'll show you the picture next time. It's a very beautiful galaxy, and since it's so nearby, you can see it very, very clearly in very clear terms, and even see the individual stars in it very easily. So there was a supernova which went off in this galaxy, and since it's close enough, we were able to catch the neutrinos coming out of the supernova in our those Super Komikonde neutrino detectors. So there were 19 neutrinos coming in over a few seconds. Usually you catch about 10 neutrinos per day coming from the sun. And those are the evidence for that the nuclear reactions happen in the sun. Then suddenly they saw one day that there were 19 neutrinos coming in over a very short period of time, and they had energy profiles very different from what you get from the sun. And then they asked around, well, they asked the astronomers asked them. Right at that moment, the supernova was observed. Not exactly at that moment. There has to be a delay because this happens first and the gases heat up. Shock waves produced after a little bit while, after a few minutes. And whatever is predicted, that was tested exactly. This is how many, although trillions and trillions and trillions of neutrinos are produced, but since they are spread over a very big circle, and since we detect only very, very tiny fraction of them, so 19 were expected, around this number was expected, and we saw them. And we found this delay which was expected. And they had exactly the profile, a spectrum, as we expected. So this was a big confirmation of our theory of stars and our this whole story that what happens in the centers and all the story about Chandrasekhar Limit. So let me stop here.